Yeah, I find
I know
it.
her with the first name, but
Yeah,
no, it's just the same.
same day actually I
Yes,
use.
same day.
Yeah, I use like that.
No, but normally you use a maiden name first name.
Yeah, I don't know.
Oh, I see. That's what was confusing me actually. Yeah, but this is good.
কোথাও কোনো লেখা নেই।
Good afternoon. Welcome to the second Hema Ramachandran lecture. And I'm delighted that Aditi agreed to come here. I mean, this was supposed to be early in the year, but Mahakumbh came in the way. And but we have now Aditi here to give the talk on quantum networks. So these series of lectures commemorate Professor Hema Ramachandran, who was a very respected colleague here, who set up the LAMP group, Light and Matter Physics group, one of the early people to, work on this area in RRI. So to take things forward, let me invite Sanjukta to talk about Hema Ramachandran and also introduce the speaker today.
Thank you, Tarun. So today we have have organized the second Hema Ramachandran lecture. This is a tribute to the great visionary and a very nice human being, which Hema Ramachandran was. Hema Ramachandran, I knew when I was doing my PhD in TFR Mumbai. And she used to visit often when we were working on our BC experiment. And her presence was always so motivating and encouraging. And I could learn a lot from her. She had very nice work on quantum optics, and I could learn a lot from her whenever we had scientific discussions. And when I joined RRI, I was fortunate again to get the affectionate and very helpful presence of Professor Hema Ramachandran. She used to go out of the way to help us in all the possible ways she could. When we had joined, she was very kind to give the lab space to us and to Saptarishi so that we could immediately get started with our experiments without losing any time, which took us for setting up the whole experiment, which we are running now. And it was not only the scientific aspects, which I have learned a lot from Hema, but also the ways of life. She taught me how to, remain cool in difficult situations, And she was always had a very calming presence, whenever she was around. And her passing away was a great loss, an irreparable loss to RRI, and which can never be replaced. So today I'm glad to, glad that we are organizing the second Hema Ramachandran lecture, and we have a very distinguished speaker for today's lecture, Professor Aditi Sende. So I introduce the speaker. Professor Aditi Sende is currently a professor at Harish Chandra Research Institute, HRI, in Allahabad, Prayagraj. And she works in the area of quantum technologies. Along with Professor Ujjwal Sen and Arun Pati, she started the Quantum Information and Computation Group at HRI in 2009. And currently the group includes herself, 2 faculty members, Debraj Rakshit, Ujjwal Sen, as well as 24 PhD students and 4 postdoctoral fellows. Professor Aditi did her doctoral work in the University of Jiangsu under Professor Marek, and subsequently was a Alexander Humboldt postdoctoral fellow with Professor Magic Levenstein, who is a very well-known person in our field of research, and in Hanover, Raman Kajol Fellow in ICFO, the Institute of Photonic Sciences in Barcelona, and an assistant professor at Jawaharlal Nehru University, New Delhi. She is a recipient of many awards, like the Booty Foundation Award for Excellence in Theoretical Physics, Astrophysics and Biophysics in 2012, Shanti Swarup Bhatnagar Prize for Science and Technology in 2018, and G.D. Birla Award for Scientific Research in 2023. Professor Aditi Sende is the Fellow of Indian Academy of Sciences and Indian National Science Academy. So with this, I have the great pleasure to welcome Professor Aditi Sende for today's lecture.
Okay, thank you very much for this introduction. Today, it's kind of always nice to come back to RRI, but today's occasion is a bit sad. In a sense, probably this is my first lecture which I am giving, this Hema Ramachandran lecture. It's a very nice initiative, but unfortunately she is no more. This is a very sad thing, and I know her almost. I first met her in 2004 when I visited RRI, and I was just finished my PhD and I came here from Germany. And as Shangjukta mentioned, that she was a renowned experimentalist and theoretician. And when I came in 2004 from Germany, there was a situation where one of our women postdoctoral fellow got a permanent position in Germany, a full professorship position which they call, and she was second theoretical physicist who got the permanent position in Germany. And then I came here, I met Hema, and she was experimentalist, and she was the kind of rare, women experimentalist in India. So she was probably one of the role models of many Indian female students and postdocs. And after that, I have many interactions with her in several occasions when I visited RRI. And actually that was not the jamana of a mobile phone. So yesterday I searched for some photos and I could not find, at least very easily. So I have a very nice memory, although, that when we have many interactions about how to implement quantum technology in real system like cold atoms and etc. I'm theoretician, so as you know that I will talk about many things where probably here there are many experimentalists sittings who differ that how really I will implement that. So I always have a very nice discussion and very good inputs I got from Hema. And so this was really a nice memory. And so when I got this invitation, I accepted immediately, but this was a bit sad for me as well. With this, I will talk about some of our works, but mainly today's talk is to motivate ourselves that, or I will try to give a flavor that why we want to build quantum technologies at all. So I will briefly talk about quantum technologies. So what is the goal, a bit literature survey, the experiments that are going on. And in particular, I will talk about quantum networks. I will talk what do I mean by quantum network, which we call quantum internet. So what is the goal and what is the literature and experiment. I will show there is something called resource entanglement, which actually is ingredient to build quantum network. And I will introduce what do we mean by entanglement. Then I will talk about briefly actually some of our recent work, where I will talk about how to spread entanglement in quantum network or internet. And there are two protocols that I will try to describe. One is measurement-based protocol, another is gate-based protocol. Now these two are different qualitatively in nature. One, as you know from our quantum mechanics class or course, that measurement means it's a probabilistic in nature, and there are gate-based which will be based on unitary operation, and so it will be deterministic in nature. Then I will talk about that if the measurement is noisy, still you can get certain benefits which actually in a real or ideal scenario you may not get. And finally, I will summarize. Okay, so let's start with a bit more a general perspective. One is quantum technologies. So I start with computer. So as we know, the classical computers, the laptops, desktop, even a powerful computer like cluster, they are quite useful in our daily life in different sectors, of course in science and technology, but in say government sector, medical, health, government institutions and so on. So then the question is why we are interested to build computer based on quantum mechanical principles. So to convince ourselves, let us consider a simple problem. So suppose I want to factorize an integer, say 45. Then I want to find out prime factors of it. And 45 has two prime factors, 5 and 3. Now, instead of 2-digit, if I go to a 4-digit number, say 1092, then the prime factors are this. Now, you can already from our experience of writing programs, we know that if I go on increasing number of digits, then it will be harder and harder to find out the prime factors, and that's intuitive. Now, how hard this will be? And you can show that if you want to find an n-digit, if I give you an n-digit integer, n is very large, then to find its prime factors, it actually the time taken or steps grows exponentially. So very mathematically, if I, more precisely if I speak, then if I want to factorize n-digit integer, then the time taken grows like that. And this is this red curve. So x-axis is the number of digits, and y-axis you can think of number of steps or time. You can map this too easily. Now it was shown in 1994, a breakthrough discovery by Peter Shor. He showed that if you want to solve this problem by using quantum mechanical principles like superpositions of quantum mechanics, then actually the time taken is of the order of this. So you see that this is polynomially. So if I want to find prime factors of an n-digit integer, then with the number of digit, the time taken actually increases polynomially. So you'll see that there is an exponential speed up that you can gain by using the principles of quantum mechanics. So this is Peter W. Shor. So around that time, there are several discoveries where it was shown that you can solve certain mathematical problems by using quantum mechanical principles much more efficiently. That means you require less number of steps, and that implies that you require less time to solve certain mathematical problems. Now, you can, I mean, these problems can be searched, like in a telephone directory, you want to find out someone's name. It can be arithmetic operation like addition or multiplication. So recently, for example, we have shown that even the mathematical problem, like mathematical arithmetic operations, like if you want to add two integer or two real number, then if you use quantum mechanics or quantum computer, then you can solve much more efficiently, and that will be more efficient if you have a noise in the system. So, but still you can ask the question that, okay, I can solve by using quantum computer certain mathematical problems, so what? But in daily life, always we don't require to solve certain mathematical problems, right? We use computer for different purposes. So I will show later in my talk that how solving this kind of mathematical problem has consequence in other fields like in quantum communication. So with this, I actually move to the part of quantum communication. So again, the communication technologies that we use, for example, internet, the mobile phone, which we use to connect with our friends, relatives, they are quite good. So why we are interested to build quantum communication, and today's talk I will try to convince you that this is worth building. So although today I will be mostly concentrated on, quantum communication, but I just want to mention that there are other devices that are also over the time that has been developed. For example, you can show that you can prepare battery based on quantum mechanics, and these quantum batteries can store more energy than the classical battery, or it will be more robust against noise, and similarly like quantum refrigerators, quantum sensors, and etc. So with this kind of, although we heard more about quantum computer and quantum communication, quantum cryptography, but there are other quantum devices that were discovered which will be quite efficient than the existing classical devices. So today, as I said, I will mostly concentrate on why we are interested to build these technologies, in particular quantum communication technology. Before I go further, I just want to, yeah.
So you are saying that the quantum refrigerator is more efficient than the classical, which means it is more efficient than carbon?
More efficient than?
Carbon.
No, not really. You cannot beat, but there are other much more subtle issues I actually kind of told in a way. I can discuss if you want. You cannot beat. There were some papers which told that you can beat, but later on it turned out to be wrong. Yeah. Okay, so this actually I just want to emphasize at this point that this building quantum technology is really revolution in technologies. So if you really prepare or build a very good lantern or candles, that research actually doesn't lead to the LED, the discovery of LED bulb or the proper bulb. Similarly, making a very good classical computer doesn't lead to a quantum computer. It will be really a different technologies, because the classical computer is based on the principle of classical mechanics, electrodynamics, electronics. On the other hand, quantum computer will be built on quantum mechanical principle, quantum mechanics. So this is really revolution in technology. So today, as I said, I will be mostly concentrated on why we are interested to build quantum communication. So already we see a kind of communication revolutions already here. As you see, this is probably when I was young or I was in college, and mostly today we are using this kind of thing, because we used to have a land phone, or we used to write letters to communicate each other, and probably here the young people sitting, they haven't even write a single letter. I'm not talking about email, just a letter and go to a post office and find nice envelopes so that you can send it and so on. So this revolution we have already seen. So today I will be discussing about some other kind of revolution, as I was talking, that it's kind of it's kind of different discoveries that we are or different kind of technology that we are going to build. So any communication protocol requires at least two parties in the picture. One is Alice, another is Bob. And suppose Alice and they are situated in two distant locations. So Alice is in Mumbai and Bob is in Allahabad. Alice can be in any other city and any other continent as well. And you can also call it Alia and Barun to make it a bit more Indianized. But here also my daughter actually complained that why Barun is with B, because it should be with V. Then I said that we are Bengali, I am Bengali, so we called it Borun, and so maybe with B. So Alia is the sender and Barun is the receiver. This we set in this picture. And suppose Alia wants to send some information from her place to Bob. Now this information can be classical. Classical, what do I mean by classical? That means suppose Alice wants to send certain information, and she can always encode that information in a strings of zeros and one, that is bit, which is the basic unit in classical computer. Otherwise, she can also, she would like to send some quantum state to Bob. So this is the quantum state means qubit, and qubit is the basic unit of quantum computer. So mathematically speaking, if you have a spin degrees of freedom, then this is the qubit, that is alpha up plus beta down. So it is arbitrary superpositions of up and down, where alpha beta are complex numbers and with a normalization. Now you can analogously think that if you have a sphere, and if the north pole represents the up spin and the south pole represents the down spin, then the surface of the sphere, all the points in the surface of the sphere represents the qubit. So mathematically speaking, it's an arbitrary element in two-dimensional Hilbert space, complex two-dimensional Hilbert space. Now one can show that if you actually use a quantum state, say in this, to send both classical and quantum information, then actually you get higher efficiency. And this was the discovery in 1992 known as quantum dense coding, when one wants to send classical information encoded in quantum state, or they want to send quantum state to Bob. And I will briefly discuss about quantum teleportation. So here Alice wants to send an arbitrary qubit to Bob. So you can think that, okay, I put it in a box and go to a post office and send it. But this is not allowed. So physical sending is not allowed in quantum teleportation. So what they will do, so if I use classical device and if I don't allow this physical sending, then you can show easily that to send an arbitrary qubit, you require infinite amount of classical communications, or in other words, infinite number of classical bits. And this can be also understood in a way, what I described, that surface of all the points in the surface of the sphere represents qubit. And in the surface of the sphere, there are infinite number of points. And so to encode this infinite number of points, you require infinite number of bits. And this is why you require in any classical device, the way we are, say by a telephone call or something, if you want to do, then you require an infinite length scale. So this is what we need. Now what is, if we use quantum state, then how will we get benefit? Now if Alice and Bob shared a quantum state a priori, then one can show that Alice can perform a measurement on her part of the pre-shared state with the input state that she wants to send, and then sends the measurement results to Bob. This is a 2 bits of classical communication. Bob can suitably perform a unitary operation and can recover the state, this input state, in his lab. So what we understand that if Alice and Bob a priori share an entangled state, then 2 bits of classical communication is enough to send an arbitrary qubit to Bob. On the other hand, if we use classical device, we require infinite number of bits. Yes?
Why your limitation is not between Alia and Varun?
Good question. I forgot. This is my old, learning and over the... So this is quantum teleportation, the famous, which was discovered 1993 by these 6 people. Now, with this, you can put another layer of complications or layer of complexity in this problem. So suppose Alice wants to send some information to Bob. Now she has to encode in such a way that no one, the third party, cannot gather any informations about the information that Alice is sending. So third party is typically called the eavesdropper. So Alice has to do the encoding in such a way that there are third party eavesdropper will not be able to gather any informations about the information that Alice is sending. On the other hand, Bob can, after receiving the information, Bob will be able to decode the message. So that's the main thing that we learn in case of cryptography, and this is extremely useful in all the internet banking, all the things that we do. So now for example, whenever we want to call someone, you got this message from the government of India that don't answer any fraud call, don't disclose, and so on. Because that's the point, that we only want to communicate any information that we want to communicate with only to our bank, not to any third party. So this is the third party, you can think of a eavesdropper. And so in case of internet banking or any kind of online shopping, it's extremely important that we have a good cryptography thing. Now all the cryptography systems that we are using nowadays, both internet banking and etc. Now the security is based on the belief that some mathematical problems cannot be solved in a classical computer in polynomial time. Now probably you can understand that why I have discussed the factorization problem in the beginning of my talk. So you know that the prime factors of a given integers cannot, the prime factorization problem cannot be solved by using existing classical algorithm in a classical computer. And that means with this algorithm, you can actually have protect the information. And that is exactly what the people were doing. And there are other also methods. But mostly this is the main thing. And so if one can build quantum computer, all the quantum current crypto systems will be insecure. And so there is a kind of threat. And so the remedy is the following, that there are quantum cryptography or quantum key distributions were discovered where the security is based on the validity of quantum mechanics, and importantly, they remain secure even when quantum computer exists. And this was initially discovered by Bennett, Brassard, and Arthur Eckert. And this cryptography, actually the scenario is quite, nice, because there are already in 2001, there was an experiment in Geneva Lake by Nicolas Gissa group, where they show, this is kind of 67 kilometer, where they demonstrated the QKD protocol under certain attack. Later on, there was a football World Cup at South Africa, which is known as Quantum Stadium Project, where also they have used quantum mechanical method to distribute ultra-secure encryption key. Now, the question is there a magic why we are getting this benefit? And this is not a magic, but this is a properties of composite quantum systems. And this composite quantum system is about entanglement. Entanglement actually plays a crucial role in all these protocols. Again, the story of two people. Probably you can recognize this picture of a movie. Anyone can recognize? No, Hamtum. Sorry. Okay. So there is a nice review article by Horodeczky's group of theory of entanglement if you are interested to learn more. So again, there are two parties, Alice and Bob, and they are situated in distant location. So if we want to perform the teleportation experiment or any teleportation or communication protocol, then the states which are useless, that states can be prepared by Alice and Bob even when they are situated in two distant locations. So that's the definition of unentangled state, and mathematically speaking, if composite system of phi AB can be written like phi A tensor product phi B, then these are the useless states. So using these states you cannot do teleportation. So suppose Alice prepares the up spin in her lab and Bob prepares the down spin in her lab, then the joint state is this. These are the useless or the product state. Now if you have the states which are useful for quantum teleportation or cryptography are the entangled states. So to prepare these states, Alice and Bob's particles should interact. So that means there should be some source which prepare the entangled state, and then source sends one particle to Alice, another particle to Bob, and then Alice and Bob can do the teleportation or cryptography experiment. So you can think that source is situated in Bangalore and source prepares the entangled state. I know Urvashi can prepare, and then source send one particle, one photon to Mumbai lab, another photon to Allahabad lab. We have to prepare, and then we can do a teleportation experiment. So she can sell some entangled states to us. And mathematically speaking, when the joint state cannot be written like phi A tensor product phi B, then these are the entangled states. So you can see that if you have again spin degrees of freedom, then these states which we learn in our angular momentum class, these are the singlet state or the triplet state, they cannot be written like that, and so they are the entangled states. Now although so this is the quantum bridge that we want to build to perform some quantum communication, quantum teleportation and cryptography protocol. Now although I have defined very easily, but it's not at all easy to detect entangled state, neither theoretically nor experimentally. So given a quantum state, it is not as yet, we still don't know a good detection criteria by which we can always tell that the state is entangled. And I think there was an important work by Urvashi and others here where they show that they develop a resource efficient method by which they can quantify entanglement and they don't require the full tomography. Now here this is a picture actually drawn by one of our MSc students. So you can think that the finding an entanglement criteria is like finding a good, good net which have a, because the entangled states can be thought of as fishes in fish, and so more, you require a finer net to really capture the small fishes. And so you have to have a good net, so you have to have a good entanglement criteria which can actually detect the noisy entangled state. And in general, in experiments, you always have a noisy entangled state. And so this is a hard problem. So anybody, the students are interested, please work. This is really, but it's an important problem. And how important it is clear from also the Nobel Prize in Physics 2022, where it was actually the Nobel Committee declared this prize for alloaspect, John Clauser and Anton Zeilinger. They were awarded this Nobel Prize and said that for experiments with entangled photon, so creating entangled state is not enough. One has to certify that the state is entangled or not. That means one has to develop the detection criteria by which you can detect the state is entangled. And here in this, they were recognized because they not only have created entangled photon, but they established that the photons are entangled by using the violation of Bell inequality. Now the question is how far we can create entangled state. So there are 2012 there was a breakthrough experiments by Anton Zeilinger group where they show that they can create or they can perform quantum teleportation, which I have discussed, over 143 kilometers. This is between two islands, La Palma and Tenerife, where they performed this experiment. I think there was a recent work from the Urvashi's group and Shatyaranjan, where they actually analyzed this, and they said that in the Indian context, how really, what will be the, if you want to do quantum key distribution between two distant locations. Now, as I said, as far as I know, that the maximum distance in which the entanglement distribution were done is between two cities, which are 1200 kilometers away, and this is by J.W. Pan's group, which is another breakthrough experiment in 2017-18. But not only in photonic system, there are also experiments in recent time where they have actually created an entangled state between two calcium ions trapped in optic valve cavities in 230-meter apart. Now this is also important that when we want to build, say, quantum computer, then in the circuit we may require to create quantum link where we require the quantum teleportation experiment between two nodes. And that, suppose I prepared this entire computing system by using trapped ions, then I also have to create, or I have to transfer some informations between the nodes, and there I have to do this, I have to create entanglement between these two nodes. And this is the, as far as I know, this is the maximum distance that they have done in trapped ions. And another experiment, actually probably one of the experiments in quantum network, where in 2022, where they have created entanglement network or entangling network by using NV centers in diamond. So in this Nature paper, they have 3 nodes and they create an entangled states by manipulating the minimum one, which I will discuss in a minute. And they create an entangled state between A and C. With this, I come to the next, maybe I have 10, 15 minutes or 10 minutes? Yeah, 15. Okay. Okay, so I will briefly describe some of our recent works. So this is first I will talk about spreading of entanglement. So what we want to, ideally we want to build quantum communication network. So these bright spots can be thought of as nodes and these links can be thought of as entangled states. So we want to connect all these nodes by an entangled link, you can think. And this is probably one of the goals in NQM, National Quantum Mission Project. So this is not at all easy because of the decoherence of the noise. So entanglement is typically fragile under decoherence, and so at the same time all the nodes are connected by entangled link is not so easy, and so this is one of the recent challenge in quantum technology. So as it was mentioned that if we really want to build quantum internet, we have to distribute entanglement across the network. So one of the first quantum network proposal, as far as I know, is by Joukowsky, Zeilinger, Horn-Eckert in 1993, where they have proposed a photonic setup to do entanglement swapping. So, this is actually the photonic setup. I am theoretician, so I made it like that. So there is, suppose, a source, and there is a receiver. Source share an entangled state with N1, and N1 share another entangled state with the receiver. Now the goal is to send or share an entangled state between S and R. Because more the distance, there will be more noise. So what we want, suppose I want from a network or a entangled shared link between Bangalore and Allahabad, which is a big distance, and so I will divide this entire distance into small parts. So suppose in between I will Nagpur, I can choose, this will be one node. And so here the sender will send share one entangled state with N1 and then this. And N1 finally performs some measurement so that S and R share an entangled state. And you can do a simple algebra and can see that this is possible. So this is actually Joukowsky, Zeilinger, Horn and Eckert. This is the photo, I think, when Zeilinger got the Nobel Prize and they together went for the prize distribution ceremony. So as I said, so you actually have you want to share an entangled state between say S and R. You divide the entire distance into small links and you share entangled state between S and N1. N1 share another entangled state with N2. N2 share another entangled state with N3 and so on. And at the same time, they perform measurement, quantum measurement in all these middle links. Finally, S and R share an entangled state. Now, it can be easy to see that if all of them share a maximally entangled state, then if N1, N2 and so on perform a Bell measurement, then S and R can share a maximally entangled state between them. But this is not, this is very ideal because experimentally these all will be a noisy state. So it's a natural question to ask that if you have a noisy entangled state shared between several nodes, then what is the critical noise so that S and R finally share some entangled state which will be useful, for example, for teleportation or QKD or etc. And it can be shown that there is something happen. Okay, so some slides have something because of the change. But anyway, so I can move a bit more. So what we show that if you have a chain of that kind of situation, so one-dimensional network, then actually you require a very good channel. That means the entangled state cannot be very noisy so that the S and R can share a highly entangled state between them. On the other hand, instead of this kind of one-dimensional chain, if you have a star network and suppose these yellow dots, these are the nodes, wants to share some entangled state, then the other nodes, the middle one perform a global measurement and all these green dots perform some local measurement like this one, okay, sorry. Then they can perform some local measurement so that finally this yellow one can share some entangled state. Now here you note that all these lines, these links, initial links are very noisy. What we show recently that if you have a kind of this kind of 1D network and here suppose this yellow nodes wants to share some entangled state, then this global measurement followed by this local measurement, then finally what is the critical noise strength that one required so that ultimately 1, 2, 3, 4 can share an entangled state. So this one has to calculate and we find that quite high noise is allowed if you, instead of a chain network, if you if you incorporate kind of star network in this scenario. And here we work out this problem also in a two-dimensional quantum network. So we ask the question how to share quantum resource in pre-decided nodes. And here all these blue dots are the nodes and all these light color are the links. So initially you have several noisy entangled state, two-party entangled states are shared, and finally we perform certain measurement to share the entangled state between this, for example, this yellow path. We also answer certain important questions in terms of Bell inequality, which I am not going to discuss. Now I consider another scenario which we call the unsharp measurement based protocol. This is interesting because this is a unsharp measurement means this is a noisy measurement. So here we will see that the noisy measurement actually help to build the network. So suppose A1 and A2 share an entangled state and A3 is a single qubit, and now A2 and A3 perform a noisy measurement. What do I mean by noisy measurements? I will tell later. But noisy measurement is actually typically happen in the laboratory. This is what I can tell now. So you A1 and A2 share an entangled state, A3 is single qubit and perform a noisy measurement, and finally you can show that there will be an entangled state shared between A1, A2 and A3. Then you take another A4 is a single qubit, perform a noisy measurement, and you create a four-party entangled state and go on. In this way, you can actually create an entangled link between n parties. And this is the example of a noisy measurement. So it's a, usually you have a, in quantum teleportation experiment, you have a Bell measurement experiment. But if Bell measurement is admixed with white noise, this is what we call by noisy measurement. And we show that there exists, in this scenario, sharing maximally entangled state is not optimal, but one actually require a non-maximally entangled state to obtain the higher entanglement between the nodes.
Sorry, is it also to preserve the monogamy, or, I mean, if you have...
Yeah, there is a monogamy present. But we are considering a multi-party entanglement. Monogamy is between the pairs. Yeah, so that is preserved. So now another example of noisy measurement. Suppose ABC shared and multi-party entangled state, and C performs a measurement. Then this link and this link got disconnected because the measurement destroyed this link. Now instead of this measurement, so this is after measurement, AB get, the entangle get concentrated on the AB link. This is very common in a quantum network, we expect that. Now instead of this measurement where you perform a projective measurement or the sharp measurement, which is an ideal situation, we recently show that if you perform an unsharp measurement or this noisy measurement in the C link, then they do not get disconnected, but they are weakly entangled. In this way, you can go on sequentially perform the measurements, and you can actually finally concentrate a high amount of entanglement in the link between A and B. And this just got published in last week. And we have shown in this scenario, just for more experts here, that if you usually, typically people think that generalized GHZ states are more highly entangled than the W states. But in this noisy scenario, we found that actually W state is more robust against noisy measurement than the GHZ state.
So when you say this unsharp measurement, is it like what is called weak measurement?
It's not really weak in a sense that weak valued measurement. It's like the measurements that I have shown that it is kind of this kind of measurement. So instead of usually in a teleportation, you do this Bell measurement. Suppose lambda equal to 1, that means this part is not there. This is the measurement you do. But your measurement apparatus is always, it cannot be isolated. So it is always noisy as well. So instead of having this measurement, actually you perform this measurement. And what we are showing that this noisy measurement is actually giving you some benefit.
It's a bit
Yeah.
counterintuitive, right? I mean, the fact that you have more noise, but that seems to be maintaining entanglement then. Or
Yeah.
because the measurement is noisy?
No,
or
it's not maintaining entanglement. So if you, suppose you perform this part, if you perform a projective measurement and you optimize over this measurement, then the concentration between AB entanglement is always very high. You cannot do with the unsharp measurement. But in unsharp measurements, since your links are not getting disconnected, you can sequentially perform the measurement. So it's not the first time you perform measurement, then you again perform the measurement depending on the output and so on. So then you have a more chance to manipulate, and if you do that, then there are highly entangled state like GHZ state, which people believe and people usually prepare for communication network. But what we are showing that in case of noisy scenario, actually it's better to prepare decay kind of state compared to the GHZ state. So last part I will talk about, so up to now I was talking about the measurement based protocol, which is actually a probabilistic, because measurement means always there is a probability involved. But now we will be talking about a guess based protocol. Suppose there are this kind of link is prepared. This may not have any geometry, but these nodes are connected. And these nodes are connected and these nodes are connected. You can think these are small quantum circuits, okay? And now these two nodes, you can perform a 2-qubit quantum gates, which is a unitary operator. And again another, these two nodes, you perform a unitary operator. So finally you get this big network. And this is exactly what the IBM recently have published, that they want to prepare small quantum clusters and they want to connect these clusters by the quantum link. This is exactly what we thought of. So these are the small quantum clusters or quantum circuits that you have prepared. Then you do a unitary operation, suitable unitary operation, so that this one is connected with this that you see here, and so on. So in this way you can actually circulate entanglement. Now you have to of course optimize over this, what is the best unitary or best quantum gate that you can perform, so that this state, finally this multipartite state is highly entangled. And in this work we have actually worked down what are the unitary operators, optimal, how the unitary operator look like. That means in other words, what are the quantum gates that one can do so that these links get connected. And this paper, this method we called an entanglement circulation method. And actually we find these optimal unitary operations to be chosen so that we can maximize entanglement in a network, and these can be implementable in quantum circuit. Now if you have even a structure like a triangular network, we found that what are the number of gates to be implemented in every step, so that finally this kind of triangular network can be done. And one can do it in square, in other lattice geometry and so on. Yes?
So what measure of multi-party entanglement are you using?
Yeah, something, yeah, I haven't discussed. This is something called genuine multi-party entanglement measure. It's called generalized geometric measure. This is one of the geometric measure. If you want, I can tell somewhere. Yeah. So this measure, the good thing is that this is computable. So this was 2010, Ujjwal and I have worked out this measure, and we found a simple way to compute these measures. So I came to the end. So I think I tried to convince you that there are protocols can be developed by which multipartite entangled state can be created in network. They can be of two types. One is measurement based, and measurement can have two types also, the real ideal measurement like projective measurements like the teleportation experiment you do, and the unsharp measurement, which is actually noisy measurement. And this can be in the same umbrella, and there can be a gate based protocol. Now the method by which you can certify entanglement is either by using Bell inequality that we did, or you calculate, or you do the complete tomography and calculate the genuine multipartite entanglement measure. And so as I have tried to tell you that quantum cryptography is already a kind of reality. There are a lot of experiments have done. There are several things still remain open, specifically from the perspective of security analysis, but still this is reality. Now, quantum internet is one of the goal now around the world. So, in National Quantum Mission, this is one of the aim to do that. And as you know, this is the National Quantum Mission which was discussed. And I think one of the thing that I talked about this quantum repeater, how you actually divide the links into several sectors. This will be done by lead PI by Urboshi, and there are other MPI, Orijit, Sandeep and Raghavendra and myself. And quantum computer is also the final aim to build. But I also want to emphasize that apart from this quantum computer and quantum communication devices, there are several quantum devices, small quantum devices that are discovered which were important and which can give better efficiency than their classical counterparts. And also what I feel as a theoretician, that apart from quantum technological aspect, this also help us, this kind of research also help us to understand quantum mechanics in a better way. That probably one of the benefit as a scientist or as a researcher. And the work that I have shown is done by the group of people. So these are the people who are working with me, masters and PhD students, and Orgo was the postdoc. And this is the entire QIC group at HRI. There are 3 faculty members, Debraj, Rakshit, Ujjwal and myself, and others are PhD and postdocs. If you are interested, you can write, visit us. And thank you very much for your attention.
Thanks for the wonderful talk. I'm sure there are questions.
Actually, there are protocol it was given. So this is a quite old concept already in the book, measurement book by Bush, Latty and Middleton. So the point is that you can think that just like a state, we always say that I want to prepare the maximally entangled state, but I prepare maximally entangled state with white noise, right? Because white noise is also an approximation. Actually, in reality, if you measure, then you will get some kind of colored noise. Similarly, suppose I want to perform in a quantum teleportation, dense coding, or all kind of quantum information protocol, the experiments where we require the Bell measurement, entangling measurement. Actually, since the measurement apparatus is always, it is always thought that the measurement apparatus is as a black box. But it's not isolated. So it will be always, instead of Bell state, it will be always a noisy state. So the noise what I have chosen here is the Bell state with a white noise, but realistically it will be some kind of colored noise. And so instead of Bell measurement, ideally, or when you do experiment, you always get that kind of states as a measurement.
Can I ask one more question? So you are looking for a quantum network on a very grand scale, but I mean, usually, I mean, we get decoherence if you are slightly, I mean, apart. So how, I mean, you at room temperature, you are planning to make this?
So, okay, so that is why I show this envy center thing. So that makes us a hopeful, although there are only 3 nodes. As I said, I apologize from the experimentalist that I can show n nodes, a very complicated link, which is easy because I am performing measurements in pen and paper. But at least the 3-node thing is the first entanglement swapping experiment in 1993 that was proposed by Zhukovsky, Zeilinger, Horn-Eckert. So even in Envy Center, where we haven't thought that people can do, there they have performed that in the middle node they perform measurement and they were able to connect the node A and C. And connect in a sense that they have some entanglement which will be useful. So you can always perform a measurement and can say that there is a connection, but they got some fruitful entanglement. So I guess that at least the 3-4 nodes is possible to do.
Right now.
Yeah, right now.
Okay.
Carrying over to Arun's question, how long are these 3-node network lived? What's the
Oh,
lifetime?
that's probably very small time.
Milliseconds?
Yeah, something like
How many?
exactly, I do not remember the
Hundreds
number.
of milliseconds? What?
No, not like that. As far as I know, I have to check.
So then, I think, as far as Arun's question is concerned, maybe you have to, you're an expert in this topic, but, in quantum computer, if we can actually envisage quantum computers with multiple qubits, they also have the same problem of decoherence. So there is, of course, very sophisticated error correction techniques and so on that theorists are actually doing. And so I think that is the reason why we believe that we will be able to employ this on a larger scale. I mean, so I think the same problem happens in computing as well. It's not a
Yeah,
repeater-specific problem, right?
yeah.
Who am I passing?
So the stability of the W state over the GHZ state, does that have to do with the higher persistence of entanglement? So you lose one qubit, it still has entanglement between the other qubits, which is not the case for GHZ. So by performing this local measurement at one site, you're effectively losing that qubit, can I think
Yeah,
of it?
but sometimes, suppose that's also sometimes is important, because suppose I can prepare or something like, say 30 qubit quantum circuit I have, right? But somehow the one qubit is noisy, so you usually discard that qubit. So instead of discarding means stressing out, theoretically speaking, instead of discarding, you can perform measurement, then you can concentrate more entanglement. And sometimes the link cutting is important, because suppose I have a 30 qubit quantum circuit, but I want to do certain operations, say arithmetic operations. For that I only need 20 qubits. So what you do, that you cut the link between all this, so that this part you perform arithmetic operation, which should not make the other circuit part may remain as it is, so that you can use it for later purpose. So
So for these
always,
things, W state will be more robust than...
yeah, that is what. Usually, typically, all the communication protocol, it is believed that the GHZ state is good. And if it is noisy, so what we are trying to say that, okay, that there will be two layers of noise coming into the picture. One is, when you prepare the state will be noisy. When you perform measurement to do teleportation or communication experiment, there will be another noise due to the measurement apparatus is noisy. So there are two noise. What we are saying, while preparing there will be noise, and probably GHZ is better, but there is a compromise, because when you have a measurement noisy, then probably preparing W can be better. That is the message that we are trying to say.
More questions?
Students do not want to ask.
You said that there are, at present we can entangle 3 qubits or something.
No,
right?
we can entangle with more qubits.
Okay.
I mean, it depends on the system. So
yeah.
as far as I know, if you have trapped N, then you can create almost 20 qubit entangled state. Although there is a 60 qubit quantum simulator recently reported, but people can correct me, because there are many experimentalists in this field sitting. And in case of, I think photon, you can have at least 12, you can entangled. So there are more qubits can be entangled.
Okay,
And I think 20 qubit also superconducting qubit they have entangled.
Okay. Yeah, so because in IBM they were allowing some 7 qubits, not 7.
No, but they
3
have the
qubits.
circuit, they are
Yes,
not
yes.
entangled. Now the
Yes,
point is, more qubit you put, entanglement, as I said, the creation or whether the system has entanglement, you have to certify, you have to verify by certain method. It's not at all easy how to certify 16 or 20 qubit entangled state. So as far as I know, in a 16 qubit trapdown experiments reported by Rainer Blood's group, you see there is a Otfried Guene, who actually was also in Maciek Levenstein's team. So I know he is kind of expert to build quantum entanglement witness operator. So he is in that paper, because in 16 qubit means you have a matrix of 2 to the power 16 cross 2 to the power 16. Now you, in an experiment, you filled up, right, the numbers. Then how will you prove that this state is entangled? Now to prove it is not at all easy. He found the entanglement witness operator particularly for that state, and he showed by that this state is entangled. So this is also another important challenge, that with a few measurements, without doing tomography, only by using few measurements, how can you prove or how can you certify multipartite entangled states?
Any more questions?
Theoretically, how do you find the, exactly follow up to the same question. So how do you ensure that all the qubits that you're talking about are entangled? Like you were talking about some method previously.
Yeah, so there are the multi-qubit, I really don't know anything. I mean, I do not know a method. The multipartite entanglement measure that he asked and I answered,
Yes, yes.
that's a genuine multipartite entanglement measure, but only for pure states. Experimentally, you will always have a noisy state, that means a density matrix. And then I really don't know efficient method. By only few measurements, you can detect entanglement by witness operator, but there is also no prescription by which you can always, given a density matrix, you can always calculate the entanglement witness operator, or you can always construct the entanglement witness operator. It's not known. So for a given density matrix, one has to find out a proper witness operator by which you can detect.
Okay, thank you.
He has a question.
Thank you, ma'am, for the nice lecture. So I have a question that in what way classical correlation is different from the quantum entanglement?
Good question. So in case of classical correlation, usually you can always detect, suppose you, I am talking about a two-dimensional space, okay? So classical correlations can be created by local operation and classical communication. This is first thing. So you can always create the classically correlated state, and you can always, this can be in only one plane. So suppose by sigma z tensor sigma z, this kind of observable, by this you can detect that. On the other hand, you have to have an entanglement detection. You should have a kind of, somehow you have to measure in a complementary direction. Like in Bell inequality, as you know, you perform a measurement, say in kind of ZZ, but you have to perform also the XX. So it's in a complementary plane where the x, sigma z and sigma x doesn't commute, as you know. So you have to do that. But it's a very, just a simple answer is you can create classically correlated state by doing something in Alice's lab and Bob's lab, followed by a classical communication, which you cannot do by you cannot create quantum correlations by LOCC, by local operation and classical communication.
And how do you quantify quantum entanglement?
That one has to go a bit bored. So there is a way to quantify entanglement. There are entanglement measure known, by which you can detect entanglement. So in case of pure state, I can do it very quickly, because in pure state, if a state is entangled, suppose there are two-party system. If the state is entangled, then the local density matrix has to be mixed. That means your purity or this mixedness can quantify entanglement. And the mixedness quantifications can be done in many ways, but probably you know from your statistical mechanics course, you can do it by entropy. So your entropy for a pure state is always 0, and entropy for mixed state is non-vanishing. So entropy of a local density matrix always can quantify entanglement for a pure state. For mixed state, it's much more complicated. This will not work, as you know, because mixed entangled state, your local density matrix is also mixed, and so the entropy will be non-vanishing. That does not guarantee that your state is entangled. You have to do another measure.
Okay, thank you.
Any more questions? if not, I have a question. So generally for an experimentalist, it's important to know the fidelity of entanglement, which depends on, the various experimental parameters. So is there a way you can, maximize the fidelity of entanglement? If you can calculate that, what is the protocol for maximizing the fidelity?
Yeah, actually in a quantum network there can be two goals. One is you optimize the fidelity of a quantum state. So it can be possible the states that we are creating, the fidelity is low. So if I consider a fidelity means you calculate the overlap between the state that you have created and the desired state. You calculate the overlap. Now the fidelity of the state can be low. We are actually demanding less. We said, okay, state may not be the same, but if we can reach to that much of entanglement, then we are happy because that entanglement can be used for certain quantum information processing tasks. So there can be two ways we can quantify. So one is that you just demand that certain quantum properties that is required for your purpose. You just see that whether the given state has that property or not. Say I know that if entanglement is positive, then I can always do teleportation experiment, and I am happy that the state that I have created has that 0.1 entanglement, right? But maybe it has a low fidelity with the maximally entangled state. On the other hand, you may require in certain situations, you may require that state to be, to be prepared. Then you consider the fidelity. So fidelity, I should say a very high demand, because if the fidelity is same, of course all the properties will be same, okay? So if the two states are same, that means fidelity is unity or one, then the states, two states property also remains same. On the other hand, fidelity can be different, fidelity can vary, but entanglement can be high. That is a less demand that we are doing. That is very nice question. The paper that I have said in this localizable, which also Torunda asked this question about Ansha measurement, where we are cutting the link by performing measurement. There actually we also have asked that question. We have shown that the fidelity is less with the maximally entangled state in every step, but the entanglement is quite high. So it's a less demanding thing.
If there are no more questions, so I invite our director, Professor Tarun Shoradeep, to hand over the token of appreciation to Professor Aditi Sendey.
Yeah, thank you. Oh, thank you.
So with this, we thank our speaker for the wonderful talk, and you are all welcome to join the high tea outside.